All right. Hi, everybody. My name is Ramses Sanchez from the University of Bonn. And today we will discuss a bit about deep generative modeling and representation learning. I hope we will have some fun, and that if you have any question throughout the lecture, please jot it down. We will have a question and answer session later on, so then we can discuss even further. I also prepare some questions and exercise for you, so please also jot them down, and then we can discuss it later. So let me start with an overview. And I want to center this whole discussion about the question of what do we mean when we say that we learn a distribution. And the main intuition that I want to convey is that we are usually minimizing a distance between probability distributions, or some sort of distance, and we will talk about that. So we will start a discussion with the classical approach, which is basically a maximum likelihood. And we will see that maximum likelihood itself can be seen as a distant minimization between distributions. And then we will, I want to mention some couple of examples where the maximum likelihood approach doesn't really work. And these are some, and we will see some of these modern problems that we are used to see with the machine learning community. So then I will introduce the deep generative models in all of their generality, but we will only focus throughout the lecture in two of these kind of models. So we will only be talking about generative adversarial networks and stochastic autoencoders. So once we introduce generative models, we will talk about the general strategy to train them, how to train these models. And again, it will be around the question of how to define a distance between distributions, the one of our data set and the one of our model. So once we have these things in mind, we can introduce generative adversarial networks. We will see why are they so difficult to train, and I will point you to the theoretical work explaining what are all of these difficulties. So we won't prove any of the theorems I'm going to be presenting. So this is more about the intuition, and I will try to give you like the relevant references. So with this thing in mind, then we will see that GANs in general also can be seen as some sort of minimization of distance between distributions. And then we will introduce the Wasserstein distance. And this is like one of the most recent approaches for generative adversarial networks, and they seem to work pretty well. And we will see some examples of the applications of these Wasserstein GANs to some real-world problems, real-world data. And here, depending on time, I plan to have a break here so that I split the lecture into parts. So the second component is going to be about representation learning, basically. So we will see how to get some knowledge about some latent variables that we're going to introduce and how we can infer them from the data. So this will lead naturally to the variational autoencoder formalism. And we will see some of the problems with this formalism. And the main thing that we want to see here is that depending on the problem that you want to solve, then there is no universal solution. So we will see that variational autoencoders are very good for some kind of problems. Also, GANs are very good for another kind of problems. And this whole lecture is about this kind of intuition. So then we will introduce yet another kind of autoencoder, the Wasserstein autoencoder, which is like very similar to the variational autoencoder. The distinction is that they basically minimize different distances. And at the end, we will see that the point here is to try to see what is the meaningful distance to minimize given the problem that we're interested in. So after this, then we will see some other recent examples and we will conclude. And yeah, I hope that you guys have fun and that, that somehow the content of this lecture is original, and yeah. So let's get started. Okay, so what does it mean to learn a distribution, right? And then imagine that you're given some data set. So we're going to call it D here and throughout the lecture, which consists of endpoints, and that these points live in some specific space. And this could be, you know, like either images or videos, speech signals, or more generally audio signals. It could also be text, like collection of documents or collection of sentences. So given this data set, we make usually two big assumptions. So the main one, the first one, is that we assume that there is, given this data, there is some hidden process that we don't know, which generates this data. And second, this is not an assumption, this is something that is actually useful for calculations, and we will see is that given this collection of points, we can somehow define the probability distribution function for this collection of points as this summation over Dirac delta functions. Yeah, so here one question that I want to start with this whole discussion is, what do we mean by saying that data set follows a probability distribution, right? So and this is what we're saying. We have some data set and that it comes from some process, but we not only say that there is some hidden process, but that this process is defined or is mathematically described by a probability distribution. And I want you to think a little bit what does this really mean, because this is, I think this is fundamental. So again, within this assumption, we are assuming that there's this IID label there, which means that the samples are independent and identically distributed. This basically means that, okay, the data points are independent from each other, but that the process generating this data set doesn't change in time as we are getting this data. So the classical approach to this problem, I mean, you know, you're a statistician, you're giving some data sets, and then you have somehow to study it. The classical approach is to think about parametric density. So we just think about density that has some sort of parameters, and then the question is, okay, so how do we learn the parameters of this density, right? So we're already making assumptions about the process, where we're saying that it has some specific density, and then we want to try to put or starting distribution close to the data set. So the most used approach is basically maximum likelihood, which simply says, let's just try to find the parameters that maximize the probability of these points according to our density, right? And it is amazing. This is more than 100 years old. One of the first papers were this, I mean, by Fisher, where he introduced this the maximum likelihood approach. And so just as a side at the second that goes along what I mean, you know, how we want to center this discussion is that maximum likelihood itself can be seen as a distant minimization. And to see this, let's just do like a short calculation. So we first, I mean, let's just introduce this Kullback Leiber divergence, which is one of the divergences that we're going to be talking about. And this is basically a functional that takes, it says how different two distributions are. The formal definition is as follows, and this was originally introduced by Kullback and Leibler again long ago. And the thing to notice is that this distribution is not symmetric, right? Because if you interchange here these two probability distributions, P of D, which is going to be the empirical probability distribution, like from our data set, and P of theta, that's going to be the distribution of our model, where theta are the parameters that we want to find, right? So what we can do here is that we can expand the log in this equation. The first term here is basically the entropy over the data set, In the second term, we can introduce or how we describe the probability distribution function for a dataset, which is this collection of Dirac functions. And if you integrate, the definition of these Dirac functions is, they're basically functionals, and then you have to integrate it against a function, and what you get is the value of a function evaluated at the center of the Dirac distribution. So if we do this thing, we basically get the first term in this next equation, and plus a constant, which is this entropy, and it's a constant because it doesn't depend on theta, which is the parameter that we want to optimize. So what we see here, this is again the maximum likelihood term that we wanted to optimize. And then what we see is that if we maximize this term, we're basically minimizing the Kullback-Leibler divergence between the empirical data set and our model. So we're literally putting these things together when we do maximum likelihood. So okay, so then let's just do a simple example. Imagine that so you are in your lab, in your company, and then you're giving some collection of data sets as these ones. And then you see, okay, I want to model this thing, and let's just try to do it in the maximum likelihood approach. So what we see is that this thing has it has two modes, and probably a good solution for this or a good model is to choose a mixture of Gaussians. Right, so where this pi here are just some sort of class probabilities, they have to pi1 and pi2, they have to add to 1, and then we have these two Gaussian centers where mu is just the mean of the distribution, so the center there, and sigma is just the variance, right? And there's the definition of the Gaussian just for reference. So if we were to do maximum likelihoods, then we will find, we will have to play a bit with this, and we will probably find something like that. And this somehow makes sense, right? So, okay, then let's just consider another example, which goes more towards the deep learning direction. So let's imagine that we are giving instead this collection of handwritten numbers, right? Like the MNIPS dataset, which is like crazy famous in machine learning. And the first thing to notice here is that, unlike before, the space, so the data space is very large, right? And one usually hears that pixels are just a sparse representation, because the combination of pixels that give a number, something that we can understand, is very particular, right? So actually, if I were just to, let's say that we have this full space of pixels, and this hypercube of 28 times 28 dimensions, and then I will just to choose randomly one point in this space. So if I just choose randomly one point, I will very likely get something like the square on the left-hand side, right? Whereas if I just sample one of the MNIPS data points, I get this number 8, right? So it will seem that from the whole space, there looks something like this, right? Like there is this whole space of points, which I will call like this calligraphic X, and the actual samples from MNIPS, they will seem to be in a sort of low dimensional piece of this space. A low dimensional manifold, right? And this is actually pretty common. There is some, so I write here, right? So there is some empirical and theoretical evidence to believe that the empirical distribution for natural images and also for speech, for example, or music, is concentrated on a low dimensional manifold. And so this is a paper that's very interesting to read. So, but the main point here, just intuitively, is that it somehow seems that the information that we need to describe MNIPS has to be way low dimensional, right? And then this is a problem, because if we have, so our classical approach is to choose the density. And the thing that, the main idea that I want to convey throughout the lecture is that if we choose a density, with the density, we cannot really represent accurately low dimensional distributions, because imagine this square here again. I don't know if you can see my mouse, but if you are out of this low dimensional manifold, the points out of there, I mean, they basically have probability 0. So if you were to describe a model that assigns probability 0 out of the manifold, then maximum likelihood wouldn't work, because we need to take the log of probabilities, right? So then this is a problem. And this is a problem that we're going to see in, I mean, for natural images is certainly there. So, okay, let's just continue. This is a completely opposite example. So here we see that the dimensionality of our data space is very low. So now we are, so this is the problem. Let's say that I'm giving you the time, this is the collection of time that you take, so for the New York taxi system. So this is the time that you take to go from one place to the other, to another place in New York. So this is going to be a distribution that is conditioned on these two covariates, right? So it's like the starting point of your trip in the taxi and the ending point. And then you will take some time to get there. If you collect all of this data, then you get this kind of distribution, right? And the thing is that, yeah, okay, so this is a low D problem, but the complexity here is in time, right? Because it is not obvious what is the right density to choose for this kind of problem. So, I mean, the question is, what should we choose here? Should we choose a gamma distribution, an exponential distribution? And then, yeah, so here, any kind of assumption that we make, any kind of parametric density that we choose, might probably not be good enough once we start taking the full complexity of the problem of the system, right? So let's just look at yet another example, and imagine now that you know there are many problems in where we can come up with equations, right? Like from physics, we can just write down a model for some specific phenomena, and here we are just modeling the predator-prey population, and this is a famous model. Is one of these. I mean, it goes into all of this set of Kolmogorov models, and it's basically defined by these two equations. We have one. There are a couple, and one of the equations describes the density of prey, and the other one the density of predators. And you see this it has some crazy assumptions in there, because I mean, because of this equation, you see that the prey population is supposed to increase exponentially unless there is an interaction between the prey and the population, but it's just a model, right? So imagine that we have this model and we have some data, and the idea is again to find the best parameters. Here are going to be this alpha, beta, delta, and gamma, and all of them are positive. And well, the densities, of course, are also positive. And the question is, how can we find this alpha, beta, delta, and gamma in so that our model fits better the data? And we're here epsilon. There are these two noise factors. I mean, and they come from a Gaussian distribution, center 0, and with variance equal to 1. So the problem with this model is that if you try to work out the density, you realize that the model itself, it doesn't really feature a density. So we cannot even, I mean, so here maximum likelihood is completely out of the question. And the thing is, so what else can we do to try to find the best parameters to fit this model to our data? So with this collection of points, let me actually summarize, right? So things that might happen is that we're looking at problems where the true data distribution lies on a low dimensional manifold, right? Like the case of NIPs or images in general, right? And again, the intuition here is that somehow the content of the image, I mean, it doesn't need that high dimensional pixel representation. And if you just add some random noise, then the whole picture wouldn't make any sense for us. So it wouldn't be a natural image. So the other point is that so yeah, we want to make these parametric assumptions. We want to choose specific densities for a problem, but then in practice, it's very difficult to come up with the right idea. I mean, there are some cases where this is doable, but there are others, like this specific example that I show, which is just like looking how long I'm going to take if I want to go from, I don't know, from Brooklyn to the Upper East Side, and I want to have some notion about this thing. This depends on where do I really take the taxi, and at what time do I actually take the taxi? How many people is in that area trying to take the taxi? So it's a crazy mess. And to try to fit a single distribution to one of these, only to the service time, it's yeah, I mean, so it's going to be very tricky, right? And the other so the other point that we somehow discussed is that it can happen that our model itself doesn't have a density. So that means that maximum likelihood is completely out of the question. So the thing is, okay, so what can we do? And what I want to do now is just to introduce this deep generative models, and the deep part comes from using neural networks, right? So again, we are given this collection of data sets, and now we're going to basically assume that there is some hidden latent space. So there is some hidden variable, and usually we will take the dimension of this latent space to be smaller than the dimension of the data. And this again goes, I mean, so this should already somehow make sense to you, because we said that for some of the problems, the data set actually is supported on a low dimensional space, right? So, so then we will assume that there's this somehow hidden space that we don't know. And then given this assumption, we will generate data. So we will have a process, a random process, and we will assume that data is basically generated in two steps. So first, we sample this latent variable from some specific distribution that usually is a simple distribution like a Gaussian, but in some cases it is, which we will maybe touch later on, where it makes sense to have like a complicated prior distribution. So we will refer to this latent space and to this P of set as a prior distribution. And then on the second step, we take this random variable and then we pass it through a function, to a parametric function. And here we will usually mean that these functions are neural networks to get a point that is again in this high dimensional space. I mean, in the space of our data set. So yes, let's just stop here for a second, and I wanted to just pose here a question, because this whole generative process approach, it's actually, it's somehow very intuitive, right? Because we're saying that there are some collection of, I mean, we assume that there are some underlying causes that basically generate the observable data set, right? So and this is good because it allows to test or intuition about some problems. We will say that there are probably 2 or 3 hidden variables, and that's also a point, right? So I said that the prior should be something simple, but in general, it could also be it doesn't have to be a single variable. It could be a collection of variables. It could be like some continuous random variable or a discrete one, or it could be a hierarchy of random variables. And this is something that I want you to think about with a specific example, right? So we said already that MNIPS is and natural images are very particular, because I mean, it appears that we cannot just choose any random collection of pixels, right, to get a natural image. So then the thing is, what would you say that is a good latent space for the MNIPS dataset? I mean, this seems like I mean, probably it's not well phrased, this question, but just try to think about it, and then it will just come up in the question answering session. So okay, then let's just get back to our problem. And then we're saying that, so we start with this low dimensional space, which we're going to call it like with this calligraphic set. And then we do this map with our function g of theta. We're going to call this function the generator. And it basically maps or space to, again, a manifold here on the data space, right? Here the little points, the black points correspond to or data points, and then this kind of pink sheet is the manifold of distribution. So this process effectively defines a distribution, and this distribution is in general supported on a low dimensional manifold. And there is a proof for this thing. I mean that if you get a random number, I mean, so you sample from a simple distribution, and then you pass it through a neural network. And if the dimension of the latent space is smaller than the dimension of your dataset, then what you will get is a distribution that is supported on a low D manifold. So this is already very interesting, because we see that we had problems where the dataset itself, I mean, it was supported on a low D manifold, and then we said that, okay, so if we have a density, we cannot really represent those kind of probability distributions. But now we have had a method, yeah, exactly, like a process to generate distributions that also live in a low dimensional space, that are supported on a low dimensional space. So then, as you can imagine, then this, of course, it doesn't make sense to train this kind of models with maximum likelihood, because you will have to choose a point. I mean, because all of the points that are out of the manifold, they had probability 0. And then you cannot compute the log of it, right? However, something that one can do here, and this is something that is important, is that sometimes, depending on how we choose our function or generator function, this g of theta map, the map can be stochastic. And if we choose it in some ways, then we might have a density after all. A good example is if we choose the map as here as follows. I mean, the map here has basically 2 components, and we are adding some noise, some Gaussian noise. So at the end, what we're getting is a Gaussian distribution that is supported on the whole of the data space. And but so if we choose this kind of transformations, then what we get is that we actually have a density. We can define a density for our final distribution, and this density is defined as in the question above the example, right? So we have to so this is going to be the marginal likelihood or evidence is how it's usually called. So, okay, then the question is, we have this kind of models with which we can generate distributions that are in a low D manifold. We also know how to get, with this same process, distributions that are supported on the whole of the data space by adding noise appropriately, right? So then the thing is, how can we train these models? So then again, so what does it mean to learn a distribution? And what we want is a way to measure somehow how close our empirical dataset P of D and or generated data, I mean, or generated distribution, how close they are, so that we can put them close them together. And there are many distance and divergences between distributions. So here we will be mainly talking about 2, which are the most used, and they're the ones that are at the moment more relevant to us. So these are going to be the Kullback-Leibler divergence that we already introduced before, and another one, that's called Wasserstein distance, which we will introduce a bit later on the game. But the main difference between these distances, I mean, how can we tell, I mean, which distance is good and what are they used for? It's usually, I mean, it usually has to do with convergence of distributions. So now imagine that we have a space of distributions, right? So we can consider a space where each point corresponds to a different distribution, right? So, and imagine that you have a sequence of distributions that I labeled them here P of theta I, right? So with I ranging from in the natural numbers. So then it is important to define this notion of convergence just for this slide, so just bear with me. So we say that a specific sequence of distribution converges if there exists some p of theta star distribution that I write here. If there's a distribution p of theta star, if it exists, so that some distance goes to 0 as we progress in the sequence, right? Of course, this definition of convergence depends on the distance. So one might imagine, for example, that we start at some distribution p of theta 0, and then and we have some sequences that converge to p of theta star under some distance that I'm going to call d1, right? So we can imagine that we have this collection of distributions and they somehow converge with this definition of convergence. The interesting thing is that I could define, one could imagine that there are other sequences, right? And these sequences do not converge under d1, but there could be another distance, d2, under which this other sequences converges. So in this case, what we say usually is that the distance d2 induces a weaker topology than d1. And the main thing so the intuition here is that, so we basically have more ways to go from p of theta naught to p of theta star. So if we have a distance that somehow induces a weaker topology, then of course we will have more ways to get to our destination, right? Which is this p of theta star, which might be what is close to our empirical data set. And so exactly, so with this intuition in mind, what we would like is to have the notion of continuity. So we have a parametric distribution p of theta, right? And what we usually do is that we want to update this parameter so that our model p of theta gets closer to our dataset, right? And ideally is that, we have access, what we do is basically to compute gradients to these parameters, right? So we will have a sequence of parameters and they will converge towards this theta star, which is the value that basically, the probably minimizes or maximizes whatever function we are optimizing, right? But the thing is that we will have continuity if given this sequence of convergence in theta in the parameter space also maps to convergence in the probability distribution space. So the thing here is that, yeah, if we have if we know a distance that somehow induces a weaker topology, so that means that we will have, it will be way easier for us to get convergence. Then with a weaker distance, then we can do this mapping easier. And if that's true, then that means that we can define as a loss this specific distance, right? Because if we can imagine this idea of continuity in probability space, then we can use the distance if the distance continues. Because we have sequences all over the place, then we can use this distance as a loss function and we can take gradients of it with respect to theta. So as a summary with this is the weaker the distance, then or the weaker the topology induced by that distance, the easier it will be to find this continuous map from the parameter space to probability distribution space. So that we can just literally change the parameters of the distribution and put the empirical dataset or model together. And here I point you to this paper on where they introduced the Wasserstein GANs, and there they discuss a bit more in detail. Why? So all of these concepts, and they show that the Wasserstein distance that we're going to introduce later on induces a weaker topology than the Kullback-Leibler divergence, and this will mean that there are going to be some cases where the Wasserstein distance is going to be continuous and the Kullback-Leibler is not going to be continuous. So, okay, we have all of these concepts about distances in mind. So let's just go to the specific examples that that we know. And So let's start with generative adversarial networks. And this is, so, you know, let's just introduce what these things are and see how do we train them and how do the concepts of this go to all of the stuff that we have said before. So let's start again with our generative model. So we have again, first step is just to sample from a simple distribution. And then the second step, we pass this latent variable from this prior distribution that here I'm already choosing it to be a Gaussian. And then we will pass it through a generator, which is this G of theta. It's going to be parametrized, I mean, it's going to be a neural network. And yes, so then we do, so G of theta is basically this map from the latent space to data space, right? And what we said before is that this kind of two-step process basically defines a distribution P of theta that in general lives on a low dimensional manifold, right? So yeah, then there is this, then there was the introduction of GANs in this paper, which I also, I mean, encourage all of you to read because it's very nicely written and very easy to follow. And the intuition that they had is also, yeah, I mean, it's very intuitive itself, yeah, right? So the thing is, imagine that you have your empirical data set, and then with our generative model, we generate a collection of points, right? Like our artificial data set. And each of these points, I mean, they come from this distribution. So the main trick is to assume, let's say that the empirical data set has a label. Let's just put it like the true label. This is the true data. And the generated data set has another label, like the false label, right? So, and we have all of these labels because we know which data point came from where. So that means that we could, in principle, train a classifier, which we will, of course, parameterize by a neural network because all of these data points are going to be in large spaces or are going to be complicated points. So the main idea is that we could train a classifier to basically say which data point comes from the empirical data set and which data point comes from the generated, from our generative model, right? And then, so as usual, if we have a classifier, what we can do is to basically write down the likelihood, right? And just train the classifier using maximum likelihood. And this is basically what we write here. So this is, you know, this is like the cross entropy. So what we're saying is we put a label, let's say 1 to the, so to the points where the data comes from the empirical distribution and a 0 when this is not the case. And then this classifier, this D of phi, is basically going to be the probability that the data point that we're looking at comes from the empirical data set. So we can take this likelihood and then we call it, so this is going to be our function. And what we do to find the best classifier is just to maximize it with respect to the parameters of the classifier. And once we have a good classifier, then we can try to minimize this function, right? So that it is trickier for the classifier to tell which of these points come from the empirical data set or the distribution. So there is this kind of competition in there. But the interesting thing is that you just take this function and try to find I mean, when one can show, and you can also look at in the original paper, that we can optimize this calligraphic L function, right? Or loss function. Here we can find what is the optimal discriminator. Let's just call it D star. And if we substitute this D star in our loss function, what we get is that the loss of the generator, what it actually minimizes, is this quantity here. So there's this two. There's this D of JS, which is called the Jensen-Shannon divergence. Is yet another divergence and some constant. So I put it here. I think I'm kind of in the middle. So yeah. Then this guy here that's the definition of the Jensen-Shannon divergence. It's defined as a function of the Kullback-Leibler divergence that we already introduced, and it's basically, I mean, it's a symmetric version of it. So the nice thing here is that what we're seeing is that for the generator, I mean, we have to optimize theta to try to put these two things together. And GAN is actually doing that. It's trying to minimize the Jensen-Shannon divergence between the empirical and the generated distribution. So, but yeah, I mean, so I'm sure that all of you have heard that if you try to do this thing in practice, it's awfully difficult to train, and people have tried to, you know, that there are a bunch of tricks and there are some intuitions around, but there's also some theory of why this happens in practice. And I want to just, you know, just point you to the direction so that you see that there is a reason why GANs are in general very tricky to train. So in this paper, what they show is that there is this theorem that's called the perfect discrimination theorem. And what they show is that if you have these two distributions, which is the empirical data set and the generated data set, and if they have disjoint support or if their support slide on low D manifolds, then you can always find optimal discriminator. So it's going just to, I mean, it's just going to be perfect in the sense that it's always going to assign like the right label to the data set. So it's always going to know which data points come from the empirical data set and which ones come from the generative model. And the thing is that, of course, then if this thing is perfect, then it will have zero gradients. So you cannot optimize it anymore. And we know, so this happens, I mean, they show that this happens for distributions that are supported on low D manifolds. And we already know that the data sets that we might be looking into, like natural images, that's the case. And we also know, I mean, there is a theorem that shows that or generated distribution is also like that, right? So this basically always holds. And then the other point, which is even more tragic, is that if as we are training our classifier and it gets closer to the optimal, then the gradients of the generator, they tend to vanish. So this is, I mean, this is terrible because, you know, so we're trying to get a classifier to be able to tell correctly which data point comes from where, so that the generator then can try to trick it, right? But as the discriminator gets better, then the gradients of the generator they go to zero, and this is also proof in this paper. So then this says like, okay, that's the reason why these things are so difficult to train. So also as a comment, in the original paper of GANs, they then modified the loss of the generator, right, a bit, and then they show that in that way that the whole training was somehow more stable. And what one see, and this also in the second paper, you should really take a look. What we see is that in that case, the generator is minimizing a different distance, so it's not the Jensen-Shannon, but it's the Jensen-Shannon plus some inverse Kullback-Leibler, and but still in the same War by Botou, what they see is that even in this case, although the gradients they do not vanish, the variance of the gradients of the generator it explodes. And then, yeah, you know, so this explains the instability. And then they also give you some sort of tricks of how to fix this thing, but it's really not so easy to train these models. So then the question is, okay, is there a way out? I mean, there has to be a way to train these models in an easier way to get all of these beautiful results that I mean, we hear all the time. And I'm going to go, I mean, so let's just, so we're going to talk about that. But first, let's just have this tiny discussion in the middle where we show that GANs in general, I mean, so before we saw it specifically in the GAN case, why that weird combination of minimax game at the end is minimizing a distance, but we can make that argument a bit more general. And this is good to understand, you know, like to get some like real understanding about the I mean, what is happening here. So then let's just introduce for a second
some divergences that are usually called F divergences, and so they are defined as follows. So this is going to be it's basically the average weight of some function, some function phi, which is convex, and that it's 0 when it's evaluated at 1. So, and we see that the Kullback-Leibler, for example, is a specific case of this of these divergences, because if you choose, for instance, this phi to be minus the log of its argument, then you get right away the KL divergence. Well, the interesting thing that I want to show you here is that okay, so this is completely generic. So phi is a convex function. So that means that we can, in general, write it that there's this Legendre differential transform to write this kind of phi functions, and it's going to be a function of its convex conjugate, which I also define here. So this is the very basics for convex optimization. I'm sure lots of you know about these things, but let's just take this thing for granted. Let's just take this specific transformation and write the function phi here as this transformation. There's going to be the support over some collection of functions V of this transformation here, right? So then, taking this expression into account, we can introduce it into our definition of F divergence as follows, right? So we're just putting this definition, this transformation inside the F divergence. We can rearrange a bit to take out the support, and then we just multiply the probabilities, and then we get something like this, right? So where F here is going to be, it's basically the collection of all functions, so that when F is evaluated at X, that value belongs to the domain of the convex conjugate of phi, right? Because if not, then this thing wouldn't make sense. But we're basically optimizing over all of the possible F. This is a large set. And what we're going to do to make this thing useful for us is, as a variational representation, we're going to replace all of this F by a parametrized set of functions F of phi, right? Where this, now the support is over this parametric family only. So that's why, now we're getting inequality because this set is most likely smaller than the original set that we started with of functions F, right? So the functions parameterized by phi is going to be smaller than the set of all functions. And so then we can write this thing in this fashion. And you see that these are basically expectation values, right? So we have an expectation value with respect to the function F of phi here. And then there's this other expectation value, but with respect with the distribution P, right? So it's and this looks pretty much like the laws for GANs. And it's interesting because that means that in general, what we can do is to choose this function F of phi as a neural network, right? So that means that we can represent any of the F divergences, like the Kullback-Leibler divergence, also this Jensen-Shannon divergence. We can write it in this way. And then if F of phi is parameterized by a neural network, and then this P of X here is just our generative model, then we can try to, again, maximize with respect to phi and minimize with respect to theta, and we basically get this adversarial game again. So just some nice references. So the first people who proposed this, as far as I know, the variational representation for F divergences is the first paper by Nguyen in the group of Michael Jordan. And the second paper are the ones, so these are the famous F GANs, right? So and they are the ones who basically introduced this variational representation introduced by Nguyen, and they frame it in the context of generative adversarial networks. So these are nice reads. And here, because this seems a bit disconnect and it seems a bit abstract somehow, but just to put it in concrete, I want to give you an exercise. And it's basically to take this convex function phi of u that I'm giving you here
and show that if you choose that phi of u here, and then you introduce this phi in our definition of the variational, in our variational representation of the distance, what we get is basically this distance here. And well, so if you see, this is basically the loss. This is the loss for the GAN. And this is a nice short exercise that I recommend you to do so that all of these concepts come into place. All right, but okay, so we've seen that GANs in general, they minimize variational representations of F divergences. We can frame the Jensen-Shannon, the Kullback-Leibler, and there are other F divergences in there, right? And but we've seen that there are all of these problems, and what I want to remind you is that we said already that it is important when our distribution or generated distribution lies on a low D manifold, then which kind of distance we're using is really relevant, because it might be that we're using a distance that makes it so difficult for this sequence of distributions that we are generating every time that we optimize our parameters to converge. It makes it so difficult to converge that then you will basically have discontinuities in your training procedure, and this is not good. So what we're going to do now is to introduce the Wasserstein GAN, which is we're going to end up with a loss function that doesn't have all of these problems. So again, we start with our same generative model. So first step, sample the random variable. Second step, we generate, we map from latent space to data space, right? And we get this implicit generated distribution P of theta. So now we're going to consider this new distance. So this is called in the literature either Wasserstein GAN distance or Earth mover distance, and yeah, it looks a bit weird. So we are here to, again, it's a constraint thing, because we have to find the infimum of a collection of functions here. So let me just define all of the pieces. The first thing here is that, so we're taking the infimum over the set of all of the possible joint distributions which have marginals either in one of and in the empirical distribution and in the generated distribution. So just to be specific, imagine that one of these, so we have one of these distributions, capital gamma, and then the density of we can define the marginal through their densities, and what we're saying is that this set of calligraphic P is the set of all of the small gammas for which these two constraints hold. So we're basically saying that the marginal over when we integrate out the X variables, we get the generated distribution, and when we integrate the other variables, we get the empirical data set. So we're trying to find the best, the map that basically minimizes the cost. So we will have some sort of cost function to move. The intuition here is that what we want to do is to take probability mass from one of our distributions, like the empirical data set, and we want to move it towards our second distribution. So what we're trying to find is the map, like this joint distribution that makes this cost function that for us in this specific case is this norm 1 distance minimum. Okay, so let's see. Later we will talk about this thing again, and probably will become more clear. If not, just jot down your questions, and we can talk about this thing more in detail. All right. So then the very important thing that so what's going to be important for us here is a corollary that comes from, again, this Wasserstein Generative Adversarial Network paper, which I also encourage you to read. So the main thing is that if our generator is a neural network, and we know that the expectation value of the norm of the random variables is finite. I mean, it doesn't diverge, which is the case if we choose a Gaussian, for example, or a uniform distribution. Then this the Wasserstein distance is going to be continuous everywhere and differentiable almost everywhere. This is, of course, a very appealing feature to have. Whereas the Kullback-Leibler and the Jensen-Shannon divergence, they are not. And then that means, so this is very good, because all of the problems that we've been saying that we have, then they're basically gone in this case. So we can then, the question is here how to compute this this distance in practice, because as you will imagine, this infimum is not, I mean, computationally is not easy to solve. And what we will do here is that there is a duality, so it's called the Cantor-Rubinstein duality, and basically rewrites our distance in this specific way, right? So I mean, at first glance, it doesn't make it any easier, but we have seen functions like this before, right? I mean, like the GAN loss function looks pretty similar to these ones. And the thing is that there is a constraint, which is like so we want to find the supremum over the set of functions, but it's not any function. It's all the functions that are one Lipschitz. And this basically means that we're looking at the functions for which their gradient is bounded by one. So I mean, if these functions are differentiable, right? But we are going to choose this f to be parameterized by neural networks. That means they're going to be differentiable. And then the constraint is going to be that, okay, so how we have to choose these functions so that the gradient doesn't is upper bounded by one. So yeah, we replace the set of functions by our parameterized functions as before. So again, this is going to be so we are not taking all of the collection of functions, just a subset. That's why we have the inequality here. And but exactly no. So how can we make sure that our neural networks our approximations for f of phi is going to be a Lipschitz function? So what we can do is just explicitly enforce the constraint on the gradient. And this was introduced by in this paper, it's called Improved Training of Wasserstein GANs, and it's very important because it gave us the ability to actually, like compute this distance so that then we can minimize it with respect to our parameter. And then we can define this. So this is going to be our loss function for the f function, which we usually call the critic. So you see that is the negative of, because we want to minimize it, we just change the signs of these two terms, and we add this penalty so that its gradient is smaller than one. But there is yet another thing, right? So the constraint of is for basically all of the space, right? So we want the function f of phi to be Lipschitz one in all of the space. And okay, so how can we do this thing in practice, right? And what they propose is to, so I wrote here some Q distribution. What they propose is basically this Q distribution is going to be defined implicitly as the, to sample from them, what you do is that you take a point from the empirical distribution, a point from your generated distribution, and then you just consider the line connecting those 2 points, and then you just sample uniformly a point in between your 2 starting points. And so this of course is going to be an approximation, because we're only ensuring that the Lipschitz constraint on these lines connecting points from our empirical and our generated distribution. But still, this seems to be, a pretty good approximation. But then, yeah, exactly. So let's just put a third question here, because I mean, I think this is important, right? So we're saying that, okay, we are connecting these points, and but the thing is, okay, how do we make sense if we are looking at discrete data? So we have or discrete sequences, you know, like if you want to do text, and you want to train it using the Wasserstein GAN. So how can you make sense of this interpolation between the points from the empirical and the generated distribution, right? And there is a way out of it, but just I mean, we can discuss about it in the question and answer session. But just think about it for a little bit. And the other important thing, I mean, this is just a technical thing, that, I mean, at least in PyTorch at the moment, as far as I know, you cannot compute a second order derivative if you're using RNNs. So this is kind of a problem for some cases, right? If you have if you are processing sequences and then you want to put them apart using this method, then you cannot use RNNs. But what we do in practice is instead use a convolutional neural network in 1D, and it also, I mean, this also works pretty well in practice. So, all right. So then let's get to a summary of this first part. Let's see how much time do we get here. And then we will make a tiny break. So yes, so what we have seen so far is that if the dimensionality of our latent space is smaller than the dimensionality of our data space, then the generated distribution is going to lie on a low dimensional manifold unless we add some sort of noise, right? And the other point that I want you to keep in mind is that the generative models are trained by minimizing distances on distribution space, and we have seen that thing in practice. Like, I mean, we saw that all of the F divergence, like the GAN is minimizing an F divergence in general, and we saw how to get an adversarial gain for any F divergence. And we have also seen that we can choose other more fancy distances like the Wasserstein distance. And what we saw is that this Wasserstein distance is continuous everywhere and differentiable almost everywhere, whereas these other F divergences like the Jensen-Shannon and the KL, I mean, are not. And this is good to have in mind. Okay, I wanted to show 3 examples of, I mean, how people use this thing in practice. And the first one is called progressive GAN. Probably you've heard of this thing. And so the first thing that I want to mention is that I think the main training part of this model it was using the Wasserstein GAN, unless instead of the standard GAN. And these images here are artificially generated images, which look pretty impressive. I mean, these people, they don't really exist. So the trick here is, I mean, or what they do is that they progressively increase the size of both the generator and the critic or discriminator as training progress. But it's I mean, I mean, we're not going to discuss like architectures or so. I mean, like my main thing here that I want to convey is that you know, there is also there is some theory component that goes only on which kind of distance we are minimizing and what does this thing mean, and this is a specific example where they use the Wasserstein GAN. So this is from the NVIDIA group, and then there's this follow-up paper by them, which I also find incredible, which is a style-based GAN. So this was also trained using the Wasserstein distance. And the interesting thing to look here, I mean, what they do, they have like imagine that they have some style variable. It's like another latent variable. I mean, one can somehow think about it in that way. And what they do is to basically pass the, so they have this two collection of images. This comes from source B. This is the first collection, and that these are also artificially generated. So these are artificial images. These are also artificial images. And what they do is basically pass some of the style and the cursor features from the style from the source B to the source A. And what we see here is like, you know, like glasses are passed by to these images, and also, but the color of the skin is preserved. You know, like long hair is also there. Pose is also in there. Is also copied, and the quality of these images is just groundbreaking. And I mean, it's just breathtaking. Is what I meant. So it's just pretty amazing, I think. And but again, this kind of examples they were trained using the Wasserstein GAN. So to actually show the third example, you know, I started like our discussion talking about this service time problem, which was basically, you know, like how long do you take when you take a taxi in New York to go from one place to the other? And we said that, yeah, I mean, to start with, it's not easy to find a good parametric function to solve this problem. So what we do instead is to, yeah, I mean, so we use a GAN. I mean, so we don't assume anything about the distribution. We just have this generative model, and we're training using the Wasserstein distance. And here there are, I mean, this is the New York example, but I also showed you another collection of examples. The first one is this, some datasets coming from GitHub, and this is basically how long do you take to solve some specific issue that you have to solve, and then this data set is there, and then we're able to model this distribution. So in all of these plots, the blue points is the empirical data set, and the yellow points are the or generated data points. We also took a Stack Overflow, and this is the time that it takes to reply a specific question. So, and this is conditioned on the tags of the question. We also have some data sets from the Bitcoin problem. I mean, we can talk about these things in the question session if you have any questions about this thing. But the thing that is for me amazing is that so these are basically 5 different time-dependent problems for fitting conditional distributions where these covariates, they also change with time. And but we're able to model all of these different problems, which have like crazily different distributions with the same technique. And this I find I don't know, quite remarkable. Okay, so let's just make a tiny break here, and then we will come back for the section on representation learning. So, but I mean, I hope to see you after this one. So let me see how can I.